Hello, my name is Sawaf. I gave this presentation as part of the Photonex Optical Metrology meeting recently in Coventry. And a few people came after the talk and spoke to Roger and myself and wondered if perhaps I could have a copy of the slides. So yes, by all means, and I thought maybe even if I record some information around the slides as well with me talking, perhaps that will give a more complete picture of the information on the slides. So what I focus on is the image processing aspects. So this is mainly speckle systems, electronic speckle interferometry systems or chirography systems. And these systems generate images like these, and these are wrapped phase maps. So this is a phase map because the pixels in the image, the intensities of those pixels represent phase information, and phase in itself is wrapped on the range of -pi to +pi, so you need to restore those multiples of 2pi, and this restoration process is called phase unwrapping, and it can be tricky because, as you can see, the location of the phase jumps, the phase wraps, is not easily determined because speckle images tend to be fairly noisy. And so you can do different things. You can try and use some filtering, like in this case a median filter, but still it's somewhat ambiguous to where exactly you add or subtract those multiples of 2pi. So phase unwrapping is tricky when you're dealing with speckle, and people have tried to use various techniques. So people have used machine learning before, but I've only come across machine learning in the last 2 years, almost by complete accident. I did this course free online at Stanford University. It was Professor Andrew Ng who since then created the Coursera platform, which you might have heard of. But what really impressed me was one of the assignments was on character recognition, and I wondered if neural networks used for that assignment could be also applied to the problem of phase unwrapping. But here, in this case, I'm really focusing on going from the wrapped phase map to the only as far as the locations of the phase jumps. So we're not going all the way from the wrapped phase map to the strain information in our chirography system, or not even to the unwrapped phase map. We're only going as far as just asking the neural network to predict or determine the locations of the phase jumps. So before the neural network can generate any predictions, you need to supply it with examples of the inputs and their corresponding outputs. So this is just a small handful of examples, just to illustrate the point. In practice, you'd use many more examples. The topology of the neural network, well, there are many topologies to choose from, but we've settled on using this topology with only having 2 layers of neurons in this neural network, and having 2 layers is enough to map any sets of inputs to any sets of outputs, even if the relationship between the inputs and the outputs is nonlinear. Having 2 layers of neurons is enough to do this mapping. Now, the number of neurons in the hidden layer correspond to the degrees of freedom which your mapping function has. So the larger the number of neurons in the hidden layer, the more degrees of freedom your mapping function has for mapping between the inputs and the outputs. The inputs in our case, we're training a 10 by 10 kernel, so 10 by 10, so we have 100 inputs. Each one of these inputs is a pixel in the wrapped 10 by 10 kernel, and the outputs also, there's 100 of these, and each output is a prediction saying that at this pixel location, is this a phase jump location or not? So yes, it's a phase jump location, or no, it isn't. Assessing the performance of the neural network, once you have trained it, assessing the performance, the accuracy of the predictions can be tricky. And here, just a few examples, 3 examples that we're looking at of wrapped phase maps, just to illustrate how assessing the quality of the prediction or the accuracy, how that can be tricky and why. So here we know what the answer is supposed to be. These are fairly straightforward examples. There's hardly any noise. Yet the predictions generated in this case are rather disappointing in terms of quality. However, if you simply take the ratio of the correct predictions versus the incorrect predictions and just compare those numbers in terms of a percentage or a ratio, the number that you obtain is rather high. This is saying it's nearly 90% accurate, which is rather flattering, considering that qualitatively, when you look at the output, it's not that good. Now, the reason for this is because the number of phase jump locations, the number of pixels in that class are far fewer than the class saying that that those locations are not phase jump locations. So the two classes are skewed, and when you have a skewed problem like this, you would do better to use a statistical measure which takes into account true positives, true negatives, false positives and false negatives, and the Matthew correlation coefficient does this very nicely. The other point to bear in mind is that the neurons in the output layer, the excitation level of these neurons can vary across the range, and if you look at it in terms of in percentage terms, the higher the excitation level in percentage terms, the more the neuron is excited, perhaps due to a strong signal in the data. So you can take the view that if you set this threshold fairly high at 85%, so you as a practitioner, it's entirely up to you where you set this threshold, and say anything at this threshold or higher means that the neuron is telling me that this is a phase jump location. So it's up to you where you set that threshold. So you can take the view, if you set it at a high level, at 85%, let's say, then you are demanding a high level of confidence in the predictions, because at that level you're that much further away from the noise floor. So if you see an excitation level at 85% or higher, this is saying that there must be quite a strong signal in the data itself. So combining the two aspects together, the confidence level with the accuracy measure, is what we call the MCC percent score, and we do this combination by we combine those two by multiplying the threshold with the MCC score. And the details of this measure is something we published recently. It's come out in the October issue of Optical Engineering, and what's even more useful about this MCC percent score is once you plot it in this way, not only does it give you an idea of the performance and the accuracy, but it also gives you intuition as to what you can do to improve that performance. So if you want to reduce the size of this gap here, you can do that by increasing the number of training examples and the variety of these training examples. And to reduce this gap here, to improve performance, what you need to do is to increase the number of neurons in the hidden layer. So this gives you intuition, as well as measuring a way to measure accuracy, and we have used it to train a 10 by 10 kernel, and after 24-25 hours of computational computation on the Amazon cloud, this was the result of that effort. And before going any further, we thought, well, we were training a 10 by 10 kernel. Is this just a relatively small, if you like, toy example, or is it something that can be really used in practice against a full field image? So before going any further, I'm trying to improve on this performance, and it's clear what we can do here to improve that performance. But before doing that, we thought, well, let's try it on a full field image, like this one here. So here we're looking at the noisy image, right? So this is computer generated. We know what the answer is supposed to be, but we're not showing that to the neural network. Instead, we're only showing it the noisy image, and we want to see how our 10 by 10 kernel performed against this 200 by 200 pixel image. So to test that, you might first try to process the image in small chunks. So you have a 10 by 10 kernel, so you take a 10 by 10 file or chunk of the image, and you process that, and then you move on and you process the next chunk, and so on. Now, this is the result that you get, and you can see here many gaps appearing. Now, those gaps are, in fact, when you look closely, you realize that those gaps are artifacts of the kernel size. So this is a fairly small kernel, 10 by 10, and so the phase jump as a structure might coincide with the edge of the kernel, and so some information will be missed out because there isn't just enough context, informational context within that kernel at that point to deduce that this is in fact a phase jump location. So these gaps that you see are just artifacts. So once you realize that, the next logical step is to move the kernel more smoothly across, 1 pixel at a time, and also horizontally and also vertically. And this gives you 2 advantages. So the first advantage is that if you look now here at the pixel at the center, the effective neighborhood size for that pixel is much larger. It's no longer only 10 by 10. Now the overall effective neighborhood size is 19 by 19 pixels. So that's one advantage. The other advantage is that once you are 10 pixels or more away from the very edge of the full field image, once you are within the central region of that image, 10 pixels away from the edge, all pixels in that area of the image receive the full 100 predictions. So for each possible location of a pixel relative to its neighbors within the 10 by 10 kernel, it will receive 1 prediction, and then also 10 by 10 kernel also 100 possible positions. So altogether each pixel receives 100 predictions, and you can accumulate those like predictions like we did here. And in here we're showing the results in a grayscale image. So the higher the intensity of a pixel in this image, the more that location, the more positive predictions that location has received, saying that yes, this is a phase jump location. You can see many of these artifacts that we saw originally with the due to the size of the 10 by 10 kernel, many of these artifacts have been overcome. There are hardly any gaps now in these results. And let's not forget that fundamentally we can improve on this still by increasing the number of training examples. You can see there is a gap in here which we can reduce by increasing the number of training examples. And also the outer triangle it represents the performance of a perfect network, which gives 100 accurate predictions, 100% accurate predictions, 100% of the time. So this is like the ideal performance. We can pursue that perfection by increasing the number of neurons in the hidden layer. So we have all these avenues which we can pursue, but at least in terms of the size of the kernel, 10 by 10, I think we've answered that question. 10 by 10 is large enough. So to summarize, and you might find this useful if you're considering to look into this area, you might would like some advice or recommendations. So I would say one thing worth trying to do where possible is to reduce the number of moving parts. So you might want to fix the the topology of the network and just settle on perhaps just using 2 layers of hidden neurons, or just pick one topology and essentially stick with it. The other thing you might want to also consider fixing is the size of the kernel. I believe 10 by 10 is large enough, so that might be worth just leaving at that size and going no larger. The things that you might want to experiment in terms of modifying and changing are the number of training examples and the variety of information contained within those training examples, and also the number of neurons in the hidden layer. The more neurons you have in the hidden layer, the more degrees of freedom the mapping function has. So that's worth experimenting with, and perhaps increasing those. Finally, looking ahead, there are other aspects which you can look to exploit to improve the performance and improve the quality of the predictions, and that's the output in terms of the phase jump locations. These locations, they are structured. They're not completely random. There is a structure there in the output. So perhaps you can exploit that some knowledge about that structure and take the view that, well, some outcomes are more likely than others. So maybe exploiting that information can help you produce better quality predictions as well. So I think it was at this point that we stopped for questions, and we had I believe 3 questions that came. The first question that we started with, somebody asked, well, people have looked at using neural networks for phase unwrapping before, but they've always come up against issues. And the question was, why is it that I feel optimistic now about the prospect of using neural network? So to respond to this question, I found my way back to the slide, and I explained that I feel optimistic because not only can we now very easily look at a good representation of the performance of the neural network and see how it's performing, but also we have this really good intuition about what we can do to improve that performance. And once we know what we need to do, the computational resources are now so abundant on the cloud, so we can go out to the cloud and hire a machine for a certain length of time at a fairly small cost. And because of this, because of having the knowledge and the resources to tackle the problem, that I feel optimistic about the prospects of neural networks for tackling this problem. Now, the second question that came was in relation to the number of neurons in the hidden layer, and somebody asked, well, would it be possible, before we start, would it be possible to predict in advance how many numbers, how many neurons do we need? So I think once we established with the person who asked the questions what they meant by that question, what I was trying to say was that essentially what you need to do is pick a number and try it and see what the performance looks like, and then plot the performance in this way, and then you might find actually the number of neurons that you have might be large enough, and the problem is in this gap that you have between the performance against the training set, which you are training the network with, and performance against the cross-validation set, which you are testing with. And what you might find is that the network is not able to generalize what it has learned from the examples that you trained it with, is not able to generalize that knowledge and use it against examples it has never seen before. And if that's the case, then increasing the number of neurons in the hidden layer will not help you overcome that problem. If that's the case, what you need to do is to increase the number of training examples and the variety of examples that you have within that training set. So that's what you need to do first. And it's only when the performance against the cross-validation set is really close, really pushing on right up against the performance against the training set, it's only when you have no more to do in that area that the only thing holding you back from achieving a performance at that point is the number of neurons in the hidden layer, and it's at that point that you want to consider increasing the number of neurons in the hidden layer. So I think that was the second question. Now the third and final question that came was in relation to the actual training set and how the training set was generated. And so the question was, okay, well, these are examples of wrapped phase maps, and they look noisy. So how was the noise added? How did we go about simulating those wrapped phase maps? So the answer was, well, we use a technique where we simulate the surface of an object, and then we add random noise to that surface, so it becomes a randomly noisy, or a noisy surface, if you like. Yeah. So a surface which has some random amount of noise added to it, and then based on top of that shape information, we then generate the various phase maps, and from that we create the wrapped phase map, and so on. So it's not that we add noise right at the end. We generate a phase map and then we add noise to it. In fact, we add noise to the information relating to the shape of the object itself, which we are simulating. And I think there was a follow-up question on, well, how much noise do we add? And the answer here is, again, different examples have different amounts of noise added, and so the amount of noise added to each of these examples is in itself a random variable. So we have a very large variety of examples with large variety of levels of noise as well. So I think this brings you right up to date to where we are with this research. If you have any questions yourselves, now you've listened to all of this, and thank you for being so patient. If you have any questions, please feel free to get in touch with myself or Roger, and we will be delighted to answer any questions you might have.